Hey guys, welcome to the third video in the thermodynamics series. In this video, we're going to take a look at how we would measure the quantity of heat that is added or removed from a system. We're also going to take a look at the natural flow of heat, or how heat moves spontaneously from one place or one system to another. So let's get into it. So you were presented a challenge at the end of the last video, which was to say, heat up a copper block and put it into a beaker of water. Now specifically, I asked you to actually use a styrofoam cup of water. Now the question was, how does the heat move? Where does the heat move? So if we were to measure the temperature of the copper block ahead of putting it into the water, and measure the water initially, and then take the final measurements after they'd been in contact with one another for a few minutes, what we'd find is that the temperature of the copper block decreased and the temperature of the water increased. Now, from our understanding of temperature as the measure of average kinetic energy of a particle, and heat as being the amount of energy that can move into or out of a system, I can therefore see that the heat moved from the object at the higher temperature, the copper, to the object at the lower temperature, the water. So we didn't have to do anything to force the heat to move. All we needed to have was a difference in temperatures. So it turns out that when you have a difference of temperature, heat will move, and it will always move in the direction of the lower temperature. This is very similar to what we talked about with pressure. Fluids move where there's a pressure difference. Heat moves where there's a temperature difference. Now, although they're different mechanisms, the idea of a difference in something from one place to another or one system to another is what causes this sort of spontaneous push of movement. Now we're going to take a look at if we can quantify how much heat moved. Now in the last video, we took a look at the effect of adding heat to a system, and what we basically said in a nutshell was that if heat is added to the system, it will cause the temperature to change, and that the temperature is a measure of the average kinetic energy of a particle in that system. We then went one step further to say that if you multiplied that average kinetic energy of a particle by the number of particles in the system, you should get the total change in the internal energy of the system, or the total amount of energy in the system. Now, in this video, we're going to take a look at a little bit more detail. Specifically, we're going to look at, does the same amount of heat added to a system result in the same change in temperature? Or are there other factors that affect that amount of heat needed to change the temperature? So in order to make this concept a little clearer, I'm going to ask you a question. Then I'd like you to pause the video and try to figure out the answer for yourself. Then come back to the video and we'll take a look at it together. So let's say that I have two beakers of water. One has 800 grams of water in it, and the other, let's say, has 300 grams. Now both are at a temperature of 20 degrees Celsius, and I'm going to apply heat to each. Now I'm going to apply the same amount of heat, if you will, and we're going to talk about how we would know that in a little bit. And then I'm going to apply it for the same amount of time. Now we do know from the last video that the temperature should increase, but our question now is, after the same amount of time, will the 800 gram water beaker have changed its temperature by the same amount as the 300 gram beaker of water? So pause the video and try to answer that. Now, if we think about that we've added the same quantity of heat to each mass of water, we do see that actually the larger mass experiences a smaller increase in temperature. So let's say over the amount of time that we added the same amount of heat to both beakers, we saw that the larger mass of 800 grams of water increased its temperature by 2 degrees Celsius. So it went from 20 to 22 degrees Celsius. Now in the same amount of time, the 300 grams of water increased about 5.5 degrees Celsius. So it went from being 20 degrees Celsius up to 5.3 or 5.5 degrees Celsius. Now let's think about why that might be the case. Well, we know that temperature is a measure of the average kinetic energy of a particle, in this case the beaker of water. Now the change in temperature would therefore reflect the change in kinetic energy of those particles. So if we've had a smaller change in temperature in the larger beaker of water, we can say that there's been a smaller change in the kinetic energy than there was in the smaller beaker of water. Now this is an indication that if we added the same amount of heat, in this case about 6,600 joules, to both of the beakers of water, we find that there really isn't as much to go around in the larger beaker as there is in the smaller one. So to keep uncovering this idea, we can say that even the two substances were the same. We knew we had water in each case. So maybe we need to do a different test. Maybe we need to take water in one beaker, let's say 800 grams of water, and then 800 grams of, say, ethanol, and apply the same amount of heat. Now they're both the same mass, should they have the same change in temperature? And what we find is that they do not. So that must mean that not only the amount of the substance matters into how much heat is needed to change the temperature, but also the kind of substance. The fact that different substances change temperature by different amounts, even when given the same amount of heat into each system, this is known as specific heat capacity. And the specific heat capacity of a material is the quantity of heat needed to raise the temperature of a unit of mass through a unit of temperature. So in other words, we might say it's the amount of heat in joules needed to change the temperature of 1 kilogram of a substance by 1 degree Celsius, or by 1 Kelvin. Now, this is not a physical chemistry class, and so we're not going to get into the reasons why different substances have a wide variety of different specific heat capacities, but what we will say is that they are different. So depending on their chemical structure, they will need a different amount of energy in order to change their temperature. In other words, in order to get their particles moving. So if we go back to the example where we had two beakers of water, both starting at the same temperature, but two different amounts of water, we saw in that case that although their specific heat capacities are the same, they did not end up with the same final temperature because they did not have the same mass. And so it goes without saying that it takes a lot more heat to raise the temperature of, say, 0.8 kilograms of water than it does to raise the temperature of 0.3 kilograms of water. More energy is needed for the larger. Now, as an interesting side note, it turns out that water actually has a very high specific heat capacity, about 4,186 joules per kilogram Kelvin. So that means it takes 4,186 joules of energy to increase 1 kilogram of water by 1 Kelvin, or 1 degree Celsius, because the difference is still 1 to 1. So if I wanted to increase the temperature of 1 kilogram of water by 1 degree Celsius, so let's say from 20 to 21 degrees Celsius, I would need 4,186 joules of energy. For a reference to how high water's specific heat capacity is, let's take a look at the specific heat of copper. Copper only takes 390 joules per kilogram Kelvin. Now that's interesting because one thing that we will see in certain courses later on is that metals and nonmetals, or polar molecules, and different situations of where molecules have different characteristics, will all experience different specific heat capacities because of their chemical makeup. Now we finally revisit our copper being added to the styrofoam cup example. Now, if you've been thinking about this carefully, you'll see that the heat should continue to move until the final temperatures are the same between the copper and the water. It's kind of like the pressure thing from fluid mechanics. When there's a pressure difference, fluids will flow, and until that pressure difference is evened out, there will always be a net force or net pressure pushing one direction. Now, although this is not exactly the same case with the same mechanism, the same idea is at work. When there's a temperature difference, the heat will naturally flow. Now, we haven't figured out exactly why that is. We've just figured out in what direction it moves and that it does happen. So we will continue to unpack that through this series. But for now, all we need to worry about is to say that the heat lost by the one substance is the same amount as the heat gained by the other. And we can use that to solve for many different things. This is called thermal equilibrium, when both have reached the same final temperature and heat flow has stopped. Now, this next topic we're just going to touch on briefly, but basically we're going to see that when a solid changes to a liquid or a liquid changes to a gas, basically whenever there's a change of phase, there's a change in the potential energy of the molecules. In other words, they've made a pretty drastic change in how they relate to one another within the system. And it turns out that this amount of energy is separate and in excess of the amount of energy that would be needed just to change the temperature. Now, in addition, we find that there is no temperature change during one of these phase changes. So in other words, the heat that is going into the system is not going in to change the temperature of the substance, but rather to change the phase. Now, it takes energy to change the phase, and so we're going to name these kinds of energy as latent heat of fusion, which is the amount of heat per unit of mass required to change the substance from the solid to the liquid phase of its melting temperature. The latent heat of vaporization is the amount of heat per unit of mass required to change the substance from a liquid to a vapor at its boiling temperature. Now, keep in mind, when we take a look at a phase changing graph where we look at temperature versus heat, we see that when temperature increases, we're in a phase where the phase is not changing. So we're in a section of the graph where the phase is not changing. But while the phase changes, the temperature stays the same. Now, this implies a very important and often highly confused point. You can add heat to a system and not change its temperature. And I'll say that one more time. You can add heat to a system and not change its temperature. This is true because there's other kinds of interactions that happen and that need to be changed, and so they take precedence at certain times based on the substance. That's why everything has a different melting or vaporization point, and we can study that in a physical chemistry class to see why it is that the molecular structure of some substance has a different point at which the amount of heat changes its phase. In the next video, we will take a look at different methods of heat transfer, as well as the zeroth law of thermodynamics. See you soon.